Good morning, everyone, and I want to welcome you to my lecture today. Uh, this I promised yesterday that I was actually going to play record a video to cover the outstanding that we have on other statistics, and that is going to be the essence of this video. Okay, give me 1 second. I'm actually going to project my screen. Okay, so what we actually have left is other statistics. Okay, so that is the last topic that I'm actually want to cover in this video. Okay, other statistics. Now, we started what we called you know um, the linear functions of random variables. But what if in a situation where we have x1, x2 up to xn, they are actually independent, and of course, we know the probability density function of them, and we know the CDF, the cumulative distribution function of that, and the x1 up to xn, they've not really been arranged. Okay, they've not been arranged whether in ascending order or descending order. It's just like you go to a party, and the way guests are sitting down, and they are not sitting according to their age. Okay, their age has not really been arranged. Of course, the way they are sitting, um that will follow a particular probability distribution that can actually call a lowercase f of x, and of course the CDF of that exists. But what if in a situation where we now try to order the sitting arrangement, well, uh, using age, and whether we are arranging that in ascending order. If you take a look at what I have here, it means this has been ordered. Right here, the first one is going to be the minimum, okay, and so on like that, and the last one here is going to be the maximum. Okay, now the question now is, um, how can we actually obtain the probability distribution of the ordered variables? Okay, we know the probability distribution of unordered variable, but after ordering them, okay, we actually were seeking to know what is actually going to be their probability distribution. I told you the other time, the x1 here is ordered and is in minimum of all the x's, and this guy here is actually the maximum. Okay, it's actually the maximum. I think I'm going to give you another example, probably from you know insurance. Okay, when you talk about the joint life insurance, a policy, for a couple, actually pays out when the first of the spouses dies, and you want to know the distribution of the minimum, okay, which is a random variable defined to be the minimum of two lifespans of the couple. Okay, I'm going to say that again. You know, you are seeking to know the distribution of minimum, which is actually going to be the random variable defined to be the minimum of two lifespans of the couple. Okay, another important example here, when you look at insurance risk. Okay, if an insurance company hold 100 policies, of which you have a cash at hand to pay 50, and you want to know the distribution of the variable, okay, x50, okay, the 50 occurrence of a payout. Okay, this is another example of other statistics. Okay, I'm going to share my screen again. Give me 1 second. I think I just lost that. Okay, so like I said, we actually needed to order the variables, okay, in ascending order, so that the x1 is going to be the minimum of that, and xn is going to be maximum of that. Okay, now we are actually, like I said, we know the PDF and the CDF of random variable that have not been ordered, and what we are actually seeking to know is actually the PDF and the CDF of the ordered random variable. Now let's assume that I want to obtain the CDF of the maximum now. Okay, the CDF of the maximum. You know, the CDF of the maximum, what we're trying to say, there's a lot that have maximum values. The maximum values actually become random variable, and we actually want to find the probability that the maximum value will actually be less or equal to a realized value. That's what we're doing right here. Okay, and you know that if you want to find the probability of the maximum less or equal to a realized value, it is the same thing as you trying to find the probability of x1 less or equal to a realized value, x2 less or equal to the realized value until you get to this. So, which is the probability of Sn less or equal to that. Okay. So, and you know what? We can actually rewrite this guy as the joint, because you know we said that x1 up to xn are independent, and if they are independent, the probability of the joint can be actually be written as the product of the respective probability, and that's exactly what we are writing right here. Okay, and then we got a lot right here. Okay, and then the numbers of this probability is actually n, and you know, since each of these, okay, represent an uppercase f, then since we have that in n times, then we're going to write f of x, okay, an uppercase f of x raised to power n. So what I'm trying to say now, the probability of xn, you know, the ordered, you know, the probability of the maximum, okay, less or equal to a realized value, is actually going to be equal to you know, the CDF, you know, the raised to power n. Okay, that is what we're gonna have. Can you guys just give me 1 second? Um, Thank you so much. I think I'm back now. Okay, so this is gonna be the CDF now, of the maximum. Okay, and you know what? The moment I know the CDF, of the maximum, of course, I can actually determine the PDF, you know, by derivative, by differentiating that. Okay, so when I differentiate this guy now, okay, so that is what I actually want to do here. So differentiating that, okay, is actually, you know, the hand is gonna come down just like that, and you know what, you're gonna this is gonna be raised to power n minus 1, then the what you have inside it will be differentiated, and automatically differentiating that is what we're gonna have. So what I'm trying to tell you right now is that that is the PDF, okay, of the maximum, why this is the CDF, okay, of the maximum. So we just obtained both the CDF of the maximum and the PDF of the maximum. Okay, in case we actually want to find the mean of the maximum, we want to find the variance of the maximum and so on like that, we can actually use that. Okay, because we can also find the expected value of the maximum, because we have a lot of maximum. Now we're going to do the same to the minimum. Okay, we want to find the CDF, okay, of the minimum, so that after getting the CDF of the minimum, then we are actually going to obtain the PDF as well, so that from there we can actually use that to conduct any meaningful inference. Okay, so in getting the CDF right now, the probability of the smallest less or equal to realized value. Of course, the probability of SL, that less or equal to, okay, for the minimum is the same thing as 1 minus the mass, the probability of S1, S2, whatever greater than that. I think you know that this guy and this guy here, they are mutually exclusive, okay? And of course, since X1, S2 up to Xn are independent, we can actually rewrite this as a product, just like what we said. And of course, when you write that as a product, from here to here, you have n numbers of that, right? So, and each of them, they are independently and identically distributed. Of course, I can write the whole of that as I can write all of that as 1 minus what I have here. Okay, so take a look at that. Okay, now that I have the CDF of the maximum, okay, now that I have the CDF of the, some of you may be wondering, if you take a look at this guy, for instance, is it as 1, okay, minus into bracket 1 minus the probability of x1 less or equal to that. I think you remember that. And we're going to have this in n time. So basically, we can actually write 1 minus into 1. Give me 1 second. You can uh, you can write okay, you can write 1 minus into 1 minus f of x and everything raised to power n, and that was the reason why we have this guy here. Okay, so what I'm trying to say right now, this is basically the CDF of the minimum, and of course, if I have the CDF of the minimum, differentiating this right now. Okay, differentiating this right now, I'm actually going to get the PDF. That's what I'm trying to do right here. Okay, trying to differentiate this guy here, and eventually I got this. Okay, so this is going to be the PDF of the minimum. Now, what am I trying to talk about right now? So you're going to see that the PDF of the minimum, which is a PDF, the minimum has already been ordered, right? It's going to be a function of the PDF and the CDF of unordered statistics. Okay, and the same thing here. If you want to talk about the PDF of Massimo, it's actually going to be written as a function of the PDF and the CDF of unordered statistics. Okay, so what I've just showcased in this slide or in this page, to walk you through how to derive both the CDF and the PDF of the minimum and maximum, okay, from group from a series of random variables that are actually independent. Okay, now I haven't done that. The next thing I want to walk you through an example right now. Okay, now that you know the PDF and the CDF of the minimum and of the maximum, then we can now revisit, some probability distribution. Now take a look at this guy here. We got x1 up to x5. Okay, and this actually they identically and independently distributed or uniform. Okay, with parameter a equal to 0 and b equal to 1. Okay, now when you take a look at this, okay, because this is actually uniform, the f of x for uniform is actually going to be 1 over b minus a. And of course, right here, you've been given b to be 1 and your a equal to 0. So it means your f of x will be equal to 1. Okay, that will be 1 over 1 minus 0, which is equal to 1. So when you have f of x equal to 1, of course, if you want to find, and that was why I actually wrote this. Look at that. F of x is actually equal to 1, where the range of x is from 0 to 1. And of course, finding the CDF of this guy now, okay, it's actually going to give me x, because finding the CDF is just to integrate 1 with respect to s, and that is going to give you this. Now, if you take a look at what I'm trying to give you right now, so this is a PDF and the CDF of unordered x1 up to x5. The x1 up to x5 has not been ordered, and if they have not been ordered and they follow uniform distribution with this parameter, okay, the f of x, the PDF is going to be this, and the CDF is going to be that. Now, based on the PDF and the CDF of unordered variable, do you know that we can find the PDF and the PDF of the maximum and that of the minimum? Okay, we can find. I'm gonna say that again. uh, you know, Given the PDF and the CDF of an other variable, you can actually find the PDF and the CDF of the minimum and maximum. Okay, the minimum and maximum when you now ordered. Okay, and I've walked you through the other time. The PDF of the maximum is actually that guy, right? And that of the minimum is actually this guy here. So we're going to make use of these two, okay, for us to be able to derive the minimum, to derive the PDF of the minimum and the maximum. Okay, if you take a look at the two, you're going to see that the PDF of the maximum and the PDF of the minimum, they are actually function of the PDF and the CDF of unordered random variable x. Okay, and you know what? If you take a look at what I have right here, okay, if you take a look at what I have right here, of course, I'm actually using the gn of x, okay, which is equal to n, okay, into f of x, okay, raised to power n minus 1, okay, f of x, okay. If you go by what we actually derive here the other time as a PDF of the maximum. So what I'm just going to do is I'm going to plug in n. What is n? Because I have x1 up to x5, okay, it means my n, okay, according to this data set, equal to 5. Okay, so I'm going to plug in that n. I'm going to plug in 5 here. That's why you have the 5, right? And what is the CDF from the unordered? Okay, the CDF, the big F of x, is actually x, right? It's actually this x. Okay, take a look at that. I'm going to plug in x to represent big L and uppercase f of x, then raised to power 5 minus 1. That's why you have s raised to power 4. And what is the f of x? Okay, the small f of x is actually 1, and that is why we have that. So multiplying that by that, okay, what we have now is 5x raised to power 4. Now, when I'm trying to tell the world right now, so using the formula right here, okay, I've been able to derive the PDF of the maximum to be 5x raised to power 4. Okay, so this is the PDF of the maximum that we have already ordered. This is different from this guy here. So we actually going to do the same to the minimum. Okay, the G of the PDF of the smallest start order is going to be n into 1 minus f of x. Okay, if you look at what we did here the other time, 1 minus that raised to power n minus 1, okay, raised to power n minus 1, then f of x. Okay, now what you just gonna do is, what is n? Okay, your n equal to 5 because you have 5 variables. Okay, I'm just gonna plug in 5. That's why I have that. Then 1 minus f of x. What is f of x? An uppercase. That is x. So it's gonna be 1 minus x. Then raised to power 5 minus 1. That's gonna be 4. You're gonna plug in f of x. Then you have 1. Okay, so that was how we got this. Okay, with the range. So what I've done now, of course, using the information here, we've been able to derive the PDF of the maximum and the PDF of the minimum. And you know what? Do you know that I can ask you to find the mean of the maximum? If you want to find the mean of the maximum, you're actually going to make use of this function. If you want to find the mean of the minimum, you're going to make use of this function, and don't forget the range. It's actually from 0 to 1, or because we're talking about uniform. Okay, so take a look at that. And of course, you can actually verify if this is correct by integrate that by showing that integral of g n the hex have to be equal to 1 over the range, or you can also do the same to the distribution of the minimum. Okay, you integrate that over the range of 0 to 1, and if it gives you 1, then it shows that they are actually correct. Because like I said, you can be asked to find the expected value of the maximum. Okay, you can be asked to find the expected value of the maximum. Okay, so if you want to find the expected value of the maximum, of course it's going to be integral the the x f of x. Okay, ds. Okay, the f of x, give me 1 second. For instance, if you want to find the expected value of the maximum, this is a PDF, right? So you're going to write the expected value of the maximum, or of that would be equal to integral x, then you're going to use gn x dx. Okay, so which means you're going to use that one, and of course you're going to use this one to for if you want to find the expected value of the minimum. Okay, so like I said, we got a lot of maximums, we got a lot of minimums, and of course you can actually find the expected, you can be asked to find the both the expected value of that and the variance. Okay, now what I'm trying to showcase right now. When you take a look, I'm trying to show you the relationship between the original PDF of unordered variable and the PDF, after the variables have now been ordered. Okay, the PDF of the maximum and the PDF of the minimum. Now, when you take a look at this guy here, it's actually horizontal. That is for uniform. Okay, that is representing the f of x. Okay, the f of x right here, of course, is a constant function, and that is the reason why at any values of x, you can see it is constant over time. Look at that. So it's constant over the range of values of x. Okay, that is actually the PDF of unordered variables. But when you take a look at the GNS, okay, this guy here, the GNS is actually the PDF of order, the maximum, and this guy here is that of the minimum. Of course, when you take a look at you know what we have here as a PDF of the maximum, you can see that's a function of x, and this guy here also a function of x, and that is the reason why you have that. So you can see that the even though three of them is actually in the range of 0 to 1, but they are not the same. Okay, so in the distribution of other statistics, you can actually, consider, we have, consider for that example, consider a case with n equal to 4, where you can actually have x or the minimum less or equal to that, and can be of the following cases. You can talk about the exactly 1 less than x, exactly 2 less than x, 3 less than x, and or 4 less than x. Okay, because you know why? Because you are considering a sample size of 4, and the sample size of 4 mean that there's a possibility, less one less than x, 2 less than x, 3 less than x, and 4 less than x. Okay, and of course for this guy here, okay, we can actually have one of the following cases for for this. Okay, don't forget these are already ordered. Okay, like the third ordered variable. So we can talk about exactly 3 are less than x, or all 4 are less than x. And of course, we can be modeled using binomial and trial, where the p equal to f of x. Okay, now if you want to start with the case 4, with the case where sample size equal to 4, okay, where you want to find the probability of x1 less or equal to 4. Okay, that is what you actually, don't forget we said using a binomial formula, the probability of the subset is actually a CDF. Okay, so that is why, so if I want to find out, here I want to find the for combination 1, the probability raised to power 1, and 1 minus that, this is like the probability of failure. So I'm going to do that from 4 combination 1 up to 4 combination 4, and what you're going to see yourself getting at the end of the day, what does it look like? This is looking like a CDF, okay, of the smallest. I'm going to show you. You remember that? That is looking at this. Look at that. That is looking at the CDF of the smallest. Okay. So which means if I plug in n equal to 4, okay, here automatically it's actually going to give me this. Look at that. So which means this is a binomial way to derive that. Okay, look at that. Okay. And then if you want to find that of the probability of x3 less or equal to x, okay, you actually going to consider for combination 3 and for combination 4. Take a look at that. When you simplify that, that's what you're going to have. Okay, and you know what, if this is going to act as the CDF. Okay, it's actually going to have as the CDF. And when you differentiate this guy right now, okay, when you differentiate this, okay, differentiate this one, differentiate that, then that's going to give you this. And what are you actually getting now? So you're getting the PDF. Okay, that's what you're actually getting now. You're getting the PDF associated with that. Okay, now, because of that, if you take a look at what we've been having, then we're going to have a general case of, looking at the behavior. Okay, right here. Okay, looking at the behavior here and the behavior here, we're going to have a general case, and the general case is going to be okay. You know what? The probability density function of, of ordered, J Sj is actually going to be gonna look at like this. If you take a look at this, this is more or less looking like a beta generated function put forward by Jones 2000 and 2004. Okay, now if you take a look at what I have right here, so this is a general representation of what I have here. Okay, for instance, if you let J to be 3. Okay, if you let J to be 3, okay, if you let J to be 3 and N, or probably to be 4, okay, you're going to see that 3 minus 1, you're going to have f of x raised to power 2, right? Okay, and don't forget that was why you have f of x raised to power 2 right here. And of course, you have small f of x. You can see here, you got small f of x, and 1 minus f of x is actually, if you take a look at this, okay, where your n equal to 4 and your j equal to 3 is just going to be 1 minus f of x, so which we have here. So what I'm trying to say now, what I have here is just a special case of this formula right here. So this formula is a generalized, is actually a generalized form of that. So what we're trying to say, when you have x1, x2, okay, up to xn, and after ordering them, of course, you expect that after ordering them, x1 is going to be the smallest, followed by that. This is going to be the maximum. Of course, these are going to be at the extreme. Okay, that was why you have 1 and j. Okay, which means for 1 and j, you're going to have for x1 and you're going to have for xn, and there's going to be a particular sj in the middle. Okay, so what we are trying to tell the world right now or here, okay, we're trying to say, okay, x3 is in the middle of the minimum and of the maximum. Okay, so that is what we have right here, okay, for the j, right? Okay, but we can also have the one, we can have a general formula for the joint. Okay, xi and sj, they have been ordered. Okay, x, we are j lie between I and n, okay, for every that. So the general formula for the joint, we're talking about the joint distribution of the ordered statistics. Okay, I'm going to say that again. So the joint distribution of the ordered statistics, but this formula right here represents the probability distribution of an ordered variable Sj, okay, an ordered variable Sj, which actually lie between the minimum and maximum. Okay, that is this is the probability distribution of that. And why this is actually the probability distribution of the two random ordered random variable that are between the minimum and the maximum, and this is a probability joint for them. Okay, so take a look at this guy here and this guy here, they are not the same. And you know what, if I now want to talk about the probability distribution of all the variables from x1 to xn, which I mean the joint probability distribution of x1, x2 up to xn, then I'm actually going to have n factorial, which is going to be the numbers of the x's, then multiply by the respective probability distribution of the x's. So I want you to take note of this to the formula. and this guy. The first one is the probability of the ordered, or SJ, that lie between the minimum and the maximum, and this is the probability of the joint. Okay, this is the probability of the joint, or the XI and SJ that that lie between the minimum and the maximum. And what I have here is the joint probability of all the X6. Okay, the independent random variable. Okay, now based on that, if for instance, if n equal to 5 and it follows uniform, and if it follow uniform with parameter 0 and 1, okay, the f of x is going to be equal to 1, because that your f of x is actually equal to 1 over b minus a. And of course, you have been told here that a comma b, so which means a equal to 0. Okay, your a equal to 0, and of course your b equal to 1, right? Okay, so if you plug that in, then you're going to have your f of s to be equal to 1. And you know what? When your f of s equal to 1, the CDF, integrating that is going to be x, right? Take a look at that. Now, you can be asked to find, if you go back to the formula right here, okay, uh, when j equal to 1, that's going to be minimum. Okay, you can use it to find j equal to 1, j equal to 2, j equal to 3, and so on like that. And so when you plug that in, and don't forget your n equal to 5. So if I want to find the distribution of the smallest now, or what I'm just going to do, I'm just going to come here, right? I'm going to plug in n to be 5 and j to be 1. And I'm also going to plug in the CDF and the PDF, okay, which is exactly what we're doing right here. And at the end of the day, look at what we got. Okay, for j equal to 2, okay, this is what you're going to get. For j equal to 3, that's what you're going to get. For j equal to 4, that's what you're going to get. For j equal to 5, and that's exactly what you're going to get. So the highest you can get for n equal to 5 is for you to get j equal to 1, j equal to 2, j equal to 3, j equal to 4, and j equal to 5. And I want to confirm to you now, this guy here is the probability distribution of the smallest, and this guy here is the probability distribution of the largest. And from G2 to G4, they are the probability distribution for the other values that lie between the smallest and the largest. Okay, I wanted to take note of that. And you know what? We can also find the joint. I told you the other time that we have a formula right here that we can actually use to find the probability of the joint of xi and sj that are already ordered. Okay, for instance, I may want to find the probability of the joint of the minimum and the maximum. Okay, I'm going to say that again. I want to find the probability of the minimum and the joint, the probability distribution of the joint of the minimum, okay, and the maximum. If I actually want to do that, you know what I'm going to do? I'm actually going to use this formula right here. Okay, I'm actually going to use that formula right there. Okay, where my I is, my I and J, my I is going to be 1. I'm going to plug in I equal to 1. I'm going to plug in J equal to 5. Okay, when I plug in I equal to 1, J equal to 5. Okay, and you're actually going to see I'm actually going to have this. Okay, you can try that. Okay, what I'm trying to say in essence here, your N is 5. Okay, that's 5 factorial. Okay, and I equal to 1 and j equal to 1, and you plug in the f of x and stuff like that. Okay, that is actually what you're going to get. Okay, and of course, this is the joint now for x1 and x5. Okay, that is a joint distribution for that. And you know what? The x1 and the x5, the x1 is less or equal to x5, and they both lie between 0 and 1. Okay, and what I'm going to show now is based on what we have found, this is a plotting different probability distribution together, the PDF of unordered variable in this distribution, and the distribution of the smallest, the distribution of when for x2, x3, x4, and the maximum. Okay, take a look at that. You can actually see they are not the same. So what I'm plotting right now is just this guy here plotting f of s equal to that, plotting the guy. Take a look at that, and that's exactly what we are trying to show. And you'll be surprised that the f of s is actually going to be horizontal. Okay, give me 1 second. Give me 1 second. As you can see, right now, you're actually going to see, uh, the shapes are not the same. Okay, take a look at that. The shape are not the same. Okay, so this is going to be the end of this material. I'm going to share another material right now. Give me 1 second. Okay, now that you have been introduced to other statistics, you know, to have a recap on what we've done in the other material, when you have random variable that are independent, that have not been ordered, that have a PDF and a CDF, we, after ordering them from the smallest to the largest, we can also derive the probability distribution of them. Okay, that is what I introduce into.